In the last section, we spoke about what happened when we lined up 5 calls to PBKDF2. The first 4 calls were each allocated to their own individual thread in the thread pool. And then groups of 2 threads were each assigned to each of our cores. Now remember, these threads can technically run at the same time, but they still have to do just as much work as they did previously. And that's why we saw it took twice as long for all the hashes to complete, because it always takes 1 second to calculate 1 hash. So if we have 4 hashes, but each core is taking twice as long to do that work, it's going to take 2 seconds total. We're now going to move on a little bit and figure out how we can work with and customize the thread pool that we see right here. So I'm going to go back over to my code editor, and we're going to add in a little bit of code to play around with a number of threads that get created anytime we start up our program. So back inside of my code editor, I'm going to go up to the very top line, and above that require statement, I'm going to update a environment variable. So I'm going to say process.env.uv threadpool size, and I'm going to set the value of that to be equal to 2. So this is going to tell libuv that whenever it creates its thread pool, it should only create 2 threads inside there. Now I'm going to save this file, and I'll rerun it at the terminal. But before I do, I want to ask you, just pause the video for a second. I want you to guess as to what effect this is going to have on our benchmark. So just think about it for a second. Okay, hopefully you've got an idea. So let's run this code and see what happens. So now we see that they are being completed in groups of 2. Well, that's interesting. Let's take a look at a diagram that summarizes what's going on. So here's our diagram. So now we have 2 of these functions, or 2 hash calls being executed at a time, because we only have 2 separate thread pools. So the first call gets assigned to thread 1. The second call gets assigned to thread number 2. Thread number 1 probably gets allocated to core number 1. Thread number 2 probably gets allocated to core number 2. And now we're back to the situation where each core only has to do 1 hash at a time. So we're back to the hashing only taking 1 second. After the first 2 hashes are complete, the next 2 calls are loaded into thread number 1 and thread number 2. Again, that takes 1 second. And then finally, after that's done, finally the 5th call can be loaded in as well. So hopefully that gives you a better idea of how we can customize the thread pool and see what happens when we decrease the number of threads that are available. Now let's do the opposite, just for fun. Let's reverse. Let's try increasing the number of threads that we have available. Let's try going up to like 5, like so. So again, I'm going to save this file, and we'll go back over to the terminal and save this and run this again. And again, I want you to kind of guess as to what's going to happen. Okay, let's run this again, and let's see. So now this time, it looks like it took quite a while, but when it eventually resolved, it took a total of about 3 seconds, and everything completed at the exact same time. So let's again look at a diagram. All right, so now here's the situation we're in now. So we've got thread 1 through 5. We have an equal number of threads to the number of hashing function calls. So each hashing function call instantly gets their own thread assigned. And now this time, we see that thread number 1, 2, and maybe 4 and 5 go to core number 2 like so. I know you can barely see these arrows, but I think you get the idea. And then you might have thought that like maybe 1 core was going to take slightly longer because it had to get the 3rd thread, right? So maybe core number 2 also had to do thread number 3 over here. And so you might have expected core number 2 to take slightly longer. But in reality, our CPU can use all the cores inside of it to juggle work between multiple threads. So when I say that, oh yeah, core thread number 1 gets assigned to core number 1, that's not entirely accurate. This OS scheduler right here kind of decides how to juggle all the work in total behind all the cores that are available. So at the end of the day, all 5 threads get roughly equal amounts of CPU time at the same time. And that's why we saw everything complete at the same time. But this time, it took about 2.5 seconds, or maybe right above that. A little bit longer than 2.5. Again, if I wasn't running my video recording software, this should have taken about 2.5 seconds. Because just as before, we have only 2 cores available. By default, it takes 1 core 1 second to process 1 hash. So when we have 5 hashes at the same time, it's going to take 2 cores, 5 divided by 2, 2.5 seconds to calculate. So again, my timings didn't quite line up with that, but if I wasn't recording my screen right now, it would have taken just about exactly 2.5 seconds. Okay, so in this section, we spoke about the existence of the libuv thread pool that is used for expensive calculations. So you're probably really curious about what functions in the Node.js library actually make use of this thread pool and about how you can use the thread pool for your own personal code. So let's start to answer those questions in the next section.